Two mechanics are elbow deep inside a heavy industrial press, clearing a jam. They cut the power, but they didn't lock the panel. Across the floor, an operator returns, assumes the stoppage is cleared, and hits start. The machine violently restarts with the crew still inside, resulting in a dual amputation. Every year, industrial workers suffer over 50,000 caught in or crushing injuries. When investigators trace the mechanical sequence of these disasters, the vast majority share a single root cause, a skipped or unverified lockout tagout procedure. We are going to forensically break down the failure patterns behind these incidents. By recognizing the exact moments where routine maintenance turns lethal, you can spot the gaps in your own isolation process before a fatal incident occurs. OSHA Standard 1910.147 establishes a strict hierarchy for controlling energy. It separates workers into two categories: affected employees, whose jobs require them to operate the machines, and authorized employees, who physically lock out the equipment to perform servicing. Fatalities happen when that boundary blurs, and nobody takes absolute ownership of the isolation process. This diagram shows a machine's energy inputs. We often assume that turning off the electricity makes a machine safe, but hazardous energy includes kinetic, pneumatic, hydraulic, and thermal sources. To achieve what safety engineers call a zero-energy state, every single one of these meters must drop sequentially to absolute zero. As you can see, the electrical power is at zero, but pneumatic pressure spikes back up. Turning a machine off without isolating all potential energy states is the single most dangerous misconception a maintenance worker can possess. Look at this conveyor belt. In our first case file, a worker rode a similar belt up to the discharge opening to clear a cardboard jam. Because he didn't shut down and isolate the energy at the point of operation, his movement triggered an automatic baling cycle sensor. Here we see an industrial concrete mixer. In a documented case, a worker entered a ribbon-type mixer like this one to clean it. He pushed a toggle switch to check the power, unaware the operator had already cut the main breaker to make a phone call. Assuming he was turning it off, the worker actually flipped the breaker back on. The operator returned and pushed the toggle to test it, activating the exposed motor while the worker was inside. This macro shot illustrates the definitive mechanical solution to that exact communication breakdown. It relies on a strict one lock, one person, one key rule. By using a group lockbox or hasp secured by 3 distinct personalized padlocks, the breaker physically cannot be flipped until every single worker has finished their job and removed their specific key. Assuming a coworker knows you are inside the machine is a fatal systemic gamble. The pattern of tragedy repeats the moment we rely on verbal confirmation instead of a physical padlock. That physical protection is frequently bypassed during what crews consider minor servicing. In one facility, workers used duct tape to hold down safety interlocks during routine tool changes. In another, a worker climbed inside a paper rewinder to replace a part and accidentally leaned on a hidden limit switch, activating the machine. This is why the correct procedure is lockout, tagout, try. Cutting the power is completely irrelevant if you do not physically attempt to start the machine to verify that the isolation worked. You have to push the start button and watch it fail. The try step is the exact threshold where a close call turns into an amputation. Trusting a switch without physically testing the equipment is a severe failure of logic. The hazard becomes even harder to track when the energy is invisible. We've seen case files where a trash compactor's suspended weight drops simply due to gravity, or a locked-out hydraulic line fires violently because of trapped compressed air. This animated cross-section of a hydraulic cylinder shows exactly how that happens. Stored potential energy, like this highly pressurized red fluid trapped behind a closed valve, remains highly volatile and completely independent of the disconnected electrical circuit. Invisible hazards are compounded by temporal failures. During group maintenance, primary locks get removed before the last worker finishes, or a shift ends, the off-going crew takes their locks off, and the oncoming crew hasn't placed theirs yet, creating a gap where an accidental restart is highly probable. Energy does not respect shift clocks. A machine left unprotected during a handoff is essentially a loaded weapon waiting for the next operator. Most LOTO fatalities stem from 5 recurring patterns: unreleased stored energy, unprotected shift handoffs, uncoordinated group maintenance, lack of verification, and the use of generic safety procedures. To counter these, the rules must be absolute. Bleed all lines to ensure off actually means dead. Never leave a machine unprotected during a shift change. Require that every exposed worker applies an individual lock, and always test the controls before beginning work. This multi-breaker array demonstrates why the lack of machine-specific procedures is the top LOTO violation. A generic policy lacks the detail to identify which specific breaker controls which machine. Without precise instructions, workers are forced to guess which switch truly isolates the hazard. This flowchart outlines the definitive 7-step life-saving sequence. Notify affected employees, shut down the equipment, isolate the sources, apply locks and tags, release stored energy, and finally, verify. That verify node is the ultimate fail-safe block before the final step, beginning the work. This sequence is supported by 3 non-negotiable prohibitions. Never remove someone else's lock, never rely on an emergency stop to protect your life, and never assume that a power switch equals safety. Implementing these 7 steps ensures that every worker returns home, proving that a zero-energy state is the only acceptable condition for maintenance. For more forensic safety breakdowns, subscribe to the channel.